In the previous video, we introduced linear subspaces and bases. Today we'll talk a bit more about the bases and then the move to study the determinants of a matrix. And so in the book, it's chapter 3.2, and then next video will be chapters 3.1 and 3.3. A linearly independent subset of Rn must have at most n elements, and a spanning set of Rn must have at least n elements. So every basis of Rn has exactly n elements. For an n-element subset V1 through Vn of Rn, the following statements are equivalent. Those vectors span Rn. These vectors are linearly independent. They form a basis. The square matrix whose columns are the vectors Vi is invertible. So let's break them down a bit more detail. So from a basis V1 through Vk of linear subspace V of Rn, we can define a linear map which sends X to a matrix which is formed, whose columns are vectors V1 through Vk, which is multiplied by the by vector X on the right. So this linear map has, by construction, range V, the big capital V, because little vi's span the big V, and it is one-to-one, since those vectors are linearly independent. A basis for V is essentially the same as a one-to-one linear map with range V. This is also called an isomorphism from Rk to V. So, and the spaces are called isomorphic. Let's talk about the size of a basis. Suppose given two bases, V1 through Vk and W1 through Wl, where a priori K and L are different integers, of the linear subspace V of Rn. Then consider this map T from Rk to Rn as before. Since T is one-to-one linear transformation with range V, there exists a unique element of Rk which maps to each of the Wi's, the pre-image. So we call it T inverse of Wi. And of course, by construction, if you apply transformation T to this vector, we'll get back Wi. So given linear dependency of these vectors, we obtain that 0 is equal to T of sum of Ci T inverse Wi, and then using linearity properties, we get this equal to Ci times Wi. So since the Wi's are linearly independent, those Ci's must be equal to 0. Right? So there's only a trivial linear combination of vectors which gives you the 0 vector. Therefore, the T inverse of Wi are linearly independent. Now, since the W's span big V, each vector Vj can be written as such, so it can be composed as the linear combination of for every j, it can be composed as the linear combination of Wi's. Now, remember that we can also understand it as by definition, it's the image of if you act with transformation T on the basis vectors Ej, we get Vj. So we can write it the T of Ej as follows. So T of Ej is equal to this combination, and then we can substitute for Wi like this, right? So it's a trivial transformation. So we compose T inverse with T. So Wi is the same as T of T inverse of Wi. And then using linear properties, we can take out this T outside. And because it's one-to-one, we can, so we have T of EJ is equal to T of this combination in the parentheses. And because it's 1-to-1, we can just ignore the T and compare the arguments in the parentheses. And that tells you that the span of those vectors T inverse of Wi contains all EJs, and therefore it contains the entire RK, right? Because EJs, they form the basis. So EJs are canonical. This is so-called canonical basis. It's vectors 1, 0, 0, 0, 0, 1, 0, 0, etc. And so on. Thus, there are as many Ws as elements of basis of Rk, i.e., k of them, right? Which is the same as number of Vjs. So the script L, which we had a couple of slides ago, is equal to k. And we have learned that every basis for a linear subspace has the same number of elements. And by definition, this common number is called the dimension of the linear space. So a dimension of the linear space is the number of basis vectors in any basis. So all bases all bases have the same number of vectors. Couple of theorems. First, rank nullity theorem. If A is a matrix with R rows and C columns, that is, determines a linear transformation from RC to RR, then the dimensions of the column space and the null space add up to C. But it's a beautiful theorem because the proof is literally one sentence. So as we know from the echelon form of this matrix, the column space has dimension equal to the number of pivot columns, and the null space has the dimension equal to the number of non-pivot columns. So we just add them together, you get C. Another one-liner, row rank and column rank. The dimension of the space spanned by the rows of a matrix is equal to the dimension of the space spanned by the columns. Well, not surprisingly, both are equal to the number of pivots. Right? It doesn't matter how you count them. So now, for the rest of this video, we'll focus on square matrix. And then the following statements are equivalent. So the matrix is invertible, rows are linearly independent, rows span, rows form a basis, columns likely linearly independent, columns span, columns form a basis, and then this transformation is 1-to-1, and this transformation is onto. So a lot of things come together when the matrix is of the square form, when number of rows is equal to the number of columns. Okay, let's make a quick review. So you pause if you need to. Is this an invertible matrix? Well, it's a clear no. Right? Well, basically, you cannot divide by 0. How about this one? Yes, right. And this is the matrix is equal to its inverse in this case. It's the identity matrix 2 by 2. How about this matrix? Well, you can use any of the properties from the previous slide. Well, so we can check this is non-invertible. So, for example, the second column is the multiple of the first one. So the columns are not linearly independent, and therefore they do not form a basis in R2. However, if you take this one, it's going to be okay, right? Columns are linearly independent. Now, it's a quick reminder. So we talked about this during the discussion, but nevertheless, is this matrix invertible? Okay, although, okay, no, yeah, so is this matrix invertible? Now, we need to look at several cases. So when A is not equal to 0, then we can do the row reduction procedure like this, multiplying the second row by A and the first by negative C. We can add them together and get this matrix here, AD, AB, 0, AD minus BC. So the invertibility implies when it sort of stands when this coefficient AD minus BC is not equal to 0. However, if A is equal to 0, we just need to check other entries, and it will be invertible if and only if B, A, and C are not both 0. So in short, the matrix is invertible if and only if AD minus BC is not equal to 0. And this brings us to the notion of the determinant of the matrix. So by definition, the determinant of the 2 by 2 matrix is this combination. So, well, let's do some calculations. So here the determinant is clearly 0. Here the determinant is equal to 1. Here it's 0. And here it's -1. So see, in 2 of those examples, the determinant was equal to 0. Some more examples. So identity matrix 3 by 3, it is invertible, right? This matrix here, which is sort of drawn in the echelon form, is also invertible, where there are 3 pivot columns. This sort of lower triangular matrix is also invertible. Again, you can sort of reshuffle those rows, and then it will look like in an echelon form. How about this? No, because first 2 rows are linearly dependent; they're equal to each other. This one, well, it's a bit more subtle, but you can check here that the third row is the factor of 2, like a factor of 2 multiple of the first row. So therefore, again, they're not linearly independent. And this one, again, so the you can check that these 2, you can add them together. Yeah, so these are also not linearly independent. The rows are not linearly independent, and therefore the matrix is not invertible. Yeah. So for example, you can multiply you can add the first row and third row and multiply second row by -2, and you'll see that they all cancel. Okay, now we looked at the example of determinant 2 by 2. Now let's look at the 3 by 3. So that brings us, so answering the question of when this matrix 3 by 3 with 9 components is invertible brings us to the notion of the determinant of the 3 by 3 matrix. And of course, the determinant exists for any square matrix. There's a combinatorial formula, but we'll talk about this some other time. Assume A is not equal to 0, and then we can do the row reduction, right? So we'd get rid of this 2 entries below A. So for example, you would multiply second row by A, second and third row by A, and then multiply the first row by -D and add it to the second row, multiply the first row by -G and add it to the third row. That's what you will get. Now this matrix is invertible if and only if the bottom 2 rows are linearly independent, right? So when these 2 rows are not proportional to each other, right? And when does it happen? So it happens if the determinant of this 2 by 2 matrix, right, 2 by 2 submatrix, right, which is formed by the bottom right 2 by 2 table, is not equal to 0, right? So let's look at this again. Over here, so we need to look at this for, so these rows are linearly independent if the determinant of this 2 by 2 matrix is linearly independent, excuse me, is not equal to 0. So we can forget about zeros, we can just focus on this 2 by 2 submatrix here. So we need to need to find the condition on these parameters such that the rows are linearly independent. right? And how to do? We know how to do this for determinants of 2 by 2 matrices. So the determinant should not be equal to 0. There's a lengthy calculation, as you can see here. So you would multiply AE minus BD by this number, and then minus AH minus BG times that number. If you like, you can open up the parentheses. It will look like this. Now, here we assume that A is not equal to 0. And so this is true that if this thing in the parentheses is not equal to 0, right? And sort of by analogy with what we talked before, so since, in other words, the condition of invertibility of the whole 3 by 3 matrix boils down to the fact that this expression here is not equal to 0, and we call this expression the determinant of this 3 by 3 matrix. So if I assume that A is not equal to 0, right, then the matrix is invertible, provided that this expression with 6 cubic terms, right, the 6 monomials with the products of 3 letters is not equal to 0. So let's try to understand a bit better how the determinants are computed. So in the 2 by 2 case, you can sort of derive this mnemonic rule. So you multiply the entries on the diagonal of the matrix, AD, and then subtract the product of matrix in it's called anti-diagonal, right? So the diagonal that goes from bottom left to top right. In 3 by 3 case, it's a bit more subtle, but you can still kind of figure it out. So you would, well, all these 6 terms have sort of nice kind of intuitive placement in the matrix. So first, with a plus sign, you would take the product of all the diagonal entries, AEI, and then again with the plus sign, you would take the bottom left, the GBF, and then plus CDH. So you kind of join this. You can think of this triangle over here. So if you have like there's a triangle formed by these entries, and here there's a triangle formed by those entries. So these triangles enter with plus signs, and then the main diagonal enters with a plus sign. And then there'll be 3 terms which will enter with a negative sign. So it will be the anti-diagonal, and then sort of the 2 triangles, which are kind of whose one of edges of which is sort of parallel to the anti-diagonal. And so it's if like this line is parallel to this line is parallel to this line. So whenever those triangles they are aligned with the anti-diagonal, you get minus sign, right? And then when they are aligned with the main diagonal, you have plus sign. This rule can be helpful in practical applications, right? So when you are faced with the determinant of an actual matrix, like with numbers in it, and you need to compute it. Now, you can proceed by induction. So for the matrix of arbitrary size, so it's this if the determinant of an n by n matrix is the sum of over all ways of choosing n entries of the matrix, such that 1 is in each row and each column of the product of those entries with some signs. Right. So just if you scroll back here, so see you take one element from first row and first column, first row. E is the element from second column, second row, and I is the element from the third column, third row. And here, sort of, you do them in different order, right? So so G is third row, first column. B is first row, second column, and so on. And there are certain sign convention which we need to understand. So here's this, here's that again. So this is the some of the contributions have plus signs, some of contributions have minus signs. So how do we figure this out? Now, given a choice of n entries in an n by n matrix, with one in each row and each column, an inversion is a pair of these entries such that the row of the first entry goes before the row of the second, right? So if this happens, then but the columns of the first is after the columns of the second. So we define the notion of inversion for the pair of entries. So in other words, if the number of sort of up arrows that you can draw connecting one entry to another. So in the 2x2 case, like there are no up arrows, like so sort of excuse me, up and right arrows. So kind of these guys are so A is to the left. So the column and row of A is to the left of the column and row of D. However, here you can draw one arrow like this, right? So you can draw an arrow which goes from bottom left to top right towards B, right? And that's why there is number 1 here. So the product BC acquires the negative sign. Okay, so same thing here. So let's draw those rows, those arrows. So here there are none. Here we can draw 2. Here we can draw 2. Here we can draw 1, 1, and here we can draw 3. So there are 3 inversions here, 1 inversion here, 1 inversion here, and then so the number of inversions in this last 3 terms is odd. That's why those guys acquire a minus sign, and the number of inversions in the first group is even. That's why they enter with a plus sign. Yeah, and that's how this works. So let's write the formula. So the sum over all, so the determinant is the sum over all ways of choosing n entries of the matrix such that 1 is in each row and each column of the product of those entries times -1 to the power of number of inversions. Or if you like, times the parity of inversions, right? If the number of inversions is even, this is the sign is plus. If the number of inversions is odd, it's the minus. So in the 2x2 case, it works like this. In 3x3 case, it works like that. Okay, so you should practice with a lot of exercises. Some of them come in the homework. So compute the determinant of this 3x3 matrix. So it should remind you probably the phone pad, right? So the numbers when you dial on the phone, right, or on an ATM machine, right? So what is the determinant of this matrix? Well, multiply the diagonal, 1 times 5 times 9, 45. Then plus this other triangle, 7 to 6. 7 times 2 times 6 is 84. Plus 4 times 3 times 8, 96. Minus 1 times 8 times 6, minus 48. Minus 2 times 4 times 9, minus 72. Minus 7 times 5 times 3 is a negative 105. Well, how much is 45 if we combine all this together? Well, so 45 minus 48 is -3. 84 minus 72 is +12. 96 minus 105 is -9. So it all vanishes, right? So the determinant of this matrix is equal to 0. Okay, now obviously the complexity of these operations, it increases with the size of the matrix. So determinant of this 6x6 matrix could look like a bit complicated. However, observe that there is this row which is contained of all zeros. So if you remember the definition, there is no way to choose an entry from each row and each column without choosing a zero. So every product in this sum, this big sum, will necessarily contain a zero. So every term in the determinant simply vanishes, and the whole determinant is equal to zero. Okay. Now, how about this? So see, it's a matrix, the upper triangular matrix. You can say it has this echelon form, right, with pivots in every column. Now, but it has, to our advantage, it has many zeros, right? And as you can see, we need to only focus on those contributions to the determinant which are non-zero. So there's only one way to choose an entry from each row and each column without choosing a zero. Which in this case means you choose the entries along the diagonal. So the determinant is simply the product of all the diagonal elements, which in this case is 720. Right. So as long as you move off the diagonal, say you want to pick, say, this number here, you have to pick one of those other zeros, which would make the corresponding contribution vanish. Okay, now rescaling a row. So what's the determinant of this matrix? If we multiply the first row by a constant lambda, or more generally, any matrix with no entries above the diagonal. Excuse me. Yeah, so right. So we'll get back. So if you rescale the row, right, so we need to multiply by the coefficient. So and then this coefficient will appear in every term, right? In every sum. So for example, we have AEI times GBF, and then everything will be multiplied by lambda. So lambda. So the whole thing, the whole determinant will also be multiplied by lambda. So let's talk more about triangular matrices. Any matrix with no entries above the diagonal, like this, right? So has the determinant which is equal to the product of the entries of the diagonal, as we saw in the previous example. Since there are no other way of selecting one entry from each row and each column without picking a zero. Okay, now, and then if we take the multiply the first element, first row by lambda, we'll get this contribution, which means that the lambda will factor out. I'm sorry, the slides were a bit switched off, but it's okay. So the determinant of this matrix is lambda times the determinant of that matrix. And yeah, it's true for a square matrix of any size, right? So rescaling a row rescales the determinant by the same factor. And each term in the determinant is a product of entries, one from each row. So therefore, containing exactly one from the rescaled row. And likewise, rescaling of column rescales the determinant by the factor which you use to rescale a column. Okay, now how about if you take in one row, one of the rows can be presented as sum of two vectors, right? So what's the determinant of this matrix? So can we sort of split it linearly in the rows, right? So A plus A prime, B plus B prime, C plus C prime in the first row, and some other entries below it. Well, we have the formula, right? The formula for the determinant, so you can just apply it. So each of those 6 contributions will have this parentheses, right? So multiplied by the product that we had before, right? So, and which means that the determinant actually factorizes as well, right? So, so this formula is true. So there is a linearity in the rows. So you can add numbers, you can multiply them, you can subtract, you can multiply them by constants. So it is true for the matrix of any size that the determinant of linear is linear in any given row or column. So if you so here we write them in rows. So we have rows, row R1, R2, and so etc. But then the kth row can be presented as a linear combination of Rk and Rk prime with coefficients A and B. Then the determinant of this matrix is equal to A times determinant of this matrix plus B times determinant of that matrix. Here's this formula again. Each term in the determinant on the left is a product of entries, one from each row, hence exactly one in the kth row. And that's how the formula is justified. So the term in the determinant to the left is the sum of A times the corresponding term in the first determinant to the right, and B times the corresponding term in the second. This applies to linearity in the rows. Right? So we have or columns, so have to sort of stick with the same row. However, what if you try to do something different? Say, it is true that matrix, the unit identity matrix is 1, 0, 0, 1 is the sum of these two, but that is the determinant. Is the following statement true for the determinants? Right, so clearly it's not the case, right? Because determinants of these matrices in the right are both 0. So the determinant is linear in one row or column at a time, but not in the whole matrix at once. Okay, so see here. Yeah, so we talked about this before. This matrix is determinant is equal to 0, right? Because we can we can subtract the first column from the second, and we'll have the rows of zeros. So let's see how it adds up. So we take, use the formula, right? Like this, same way as we did this before. And yeah, so there's a direct cancellation. So there's a plus 12 minus 12, plus 24 minus 24, plus 15 minus 15, and everything cancels off. So any matrix with a repeated row has determinant 0. As in the previous example, to say the repeated rows are in positions I and j, then for any term in the determinant, say with the selected entries in positions ix and jy, there will be another term with the same selected entries in rows except I and j, in all rows except an I and j, and in these rows the entries are iy and jx. And because of the rule, right, so of the inversions, these two contributions will enter with the opposite signs, right? So the i's and j rows are the same. So the terms are the products of the same numbers. But one of them will enter with plus sign, the other will enter with the minus sign, because one will have one more inversion than the other. And so it will have one more arrow that goes bottom left to top right, so they will cancel. Okay, now how about these two? Determinant of matrix 1, 2, 3, 4, and 3, 4, 1, 2. So so the first one is 2. The first determinant is negative 2. The second determinant is 2. So we swap the rows. What happens when we swap rows? The determinant switches signs, right? So if here the rows go in sequence R1, R2, R3, etc. So if you swap first and second row, we get the minus sign here. And the reason for this is sort of similar to what we just discussed. if you consider the term in the expansion of the determinant for the matrix on the left, so say it contains entries 1x and 2y. So x and y are just the numbers of the entries in the first row and second row, respectively. And the term on the right containing entries, so 1y and 2x, all at the same time. It's a product of the same numbers and all the same inversions, except that 1x and 2y itself is an inversion if and only if 1y and 2x is not, right? So there's an extra sign that comes in this way. Yeah. So how about linear transformations? If we add a multiple of one row to another, so take determinant of the matrix with rows R1 through Rn, and then replace it with this matrix, where the second row is R2 plus CR1. Well, from linearity, you can deduce that this is the case. But because these matrices this matrix has two repeated rows, R1 and R1, as we discussed, this determinant will vanish. So therefore, the determinant will not change if we do the linear combination of the rows. Okay, now let's talk about computing the determinant by the row reduction. So we have learned the following facts. Swapping rows negates the sign of the determinant. Rescaling a row rescales the determinant by the same factor. And adding a multiple of a row to another does not change the determinant. Determinant of a triangular matrix, in particular if it's an echelon matrix, is the product of the diagonal entries. So in order to compute the determinant of a matrix, we first row reduce it and then keep track of any row switches of or rescaling of rows, right? Because that would that will affect the sign. It may affect the sign. And in the end, we multiply together the inverses of the row rescaling factors, the diagonal entries of the final echelon matrix, and this -1 to the number of row swaps. And this will be equal to the determinant of the original matrix. So it will be much faster than summing all the terms without doing any simplification. So that's how a computer is doing it, for example. Now, those elementary matrices that manifest the row reduction, we know what their determinants are. So if EAM, ESwap, and EScale of lambda are elementary matrices for the swap two rows, so for add a multiple of any other row, one row to another, swap rows, and rescale lambda respectively, then as we discussed, the adding multiple of a row to another does not change the determinant. So the determinant of this matrix is 1. Determinant of the swap matrix is -1, and determinant of the scaling matrix is lambda. And then from the previous slide, each is row reduced to the identity in one move, and the determinant of this identity is 1, and the effect of that on move is as we discussed above. So when we have the product of those elementary matrices, and if M is any square matrix, then the determinant of the product in this order is equal to the product of the determinants. And so this again sort of follows from what we have learned above, right? So each row operation changes the determinant by multiplying the determinant of the corresponding by the determinant of the corresponding elementary matrix. So theorem, a matrix is invertible if and only if its determinant is non-zero. Proof, the determinant of a matrix is a non-zero multiple of the product of the diagonal entries of its row-reduced version. So based on what we learned about invertibility, the statement follows. So this is non-zero if and only if the pivots run down the diagonal. So there is one pivot in each row and each column, or the matrix is invertible. Now, if matrices are invertible, two matrices A and B are invertible, then we can several identities are true. So if you multiply them in this order, B inverse A inverse A inverse B, so this is equal to 1 to the identity matrix 1 or I, or if you multiply them in this order. So here sort of A inverse A is 1, and then we can move it up front, and then B inverse B is 1. So this is 1, and similar here, B inverse is 1 and A inverse is 1. So because of this, AB is invertible and B inverse A inverse is also is its inverse. So in other words, when you do the inversion of the product of the matrices, you need to swap the order of the matrices in the product. So AB inverse is B inverse A inverse. So if they're square matrices, then it's enough to guarantee that they're both invertible. And finally, let's talk about determinants in products. So if A and B are any two square matrices, then the product of determinants of these matrices is equal to the determinant of the product. So if any of these matrices is non-invertible, then both are 0. Now, if the matrices are invertible, then A and B can each be row reduced to the identity, right? And that means that we can write A as the product of this elementary row reduction matrices, and B as the product of other elementary matrices. And then we can just compose them together like this. So we saw before that the determinant of this product of matrices is equal to product of their determinants, from where it follows that that A that B is equal to that AB.